Have you ever wondered why we crave candy? It's a question that has intrigued scientists and laypeople alike for generations. The allure of that sweet taste is almost universal, transcending cultures and ages. It's simple. Our bodies, like all living things, need sugar to survive. Glucose, a form of sugar, is a primary energy source for our cells. Whether it's from a piece of fruit or a sugary treat, our bodies break it down to fuel our daily activities. But there's a dark side to this sweet tooth. While sugar is essential, overconsumption can lead to serious health issues. Obesity, diabetes, and heart disease are just a few of the problems linked to excessive sugar intake. Cancer cells, those rogue agents of our own bodies, crave sugar too. They are particularly voracious, consuming glucose at a much higher rate than normal cells. In fact, they need it to grow and spread. This rapid consumption of sugar fuels their uncontrolled growth, making them even more dangerous. This isn't just a biological curiosity, it's a critical aspect of cancer research. Understanding how cancer cells metabolize sugar can lead to new treatments and therapies. Cancer is the second leading cause of death in the United States. The statistics are sobering, but they also drive the urgency of ongoing research and medical advancements. We are in a constant battle against this disease. Every day, scientists and healthcare professionals work tirelessly to find new ways to combat cancer, offering hope to millions of patients and their families. We've made progress in understanding and treating cancer, but the fight is far from over. We need new weapons, new strategies to combat this relentless enemy. One promising avenue of research focuses on cancer's insatiable hunger for sugar. By understanding how cancer cells metabolize sugar differently than healthy cells, we can exploit this weakness. We can starve them. In 1924, a German scientist named Otto Warburg made a groundbreaking discovery. He observed that cancer cells consume sugar at an alarming rate, far exceeding the needs of healthy cells. Even more surprising, cancer cells break down sugar in a very inefficient way, even when oxygen is plentiful. This process, called aerobic glycolysis, became known as the Warburg effect. Healthy cells prefer to break down sugar completely, in the presence of oxygen, to extract the maximum amount of energy. Cancer cells, however, take a shortcut. They convert sugar into lactate, a waste product. This inefficient process yields far less energy. Why would cancer cells choose such an inefficient path? The answer lies in their need for rapid growth. The Warburg effect provides cancer cells with the building blocks they need to proliferate uncontrollably. Section 5. Exploiting the sweet tooth PET scans and cancer detection. PET scans have revolutionized the way we detect and diagnose cancer, offering a non-invasive method to visualize the metabolic activity of cells within the body. The Warburg effect, which describes how cancer cells consume glucose at a much higher rate than normal cells, has already had a major impact on cancer diagnosis. This phenomenon is the cornerstone of PET scan technology. Positron emission tomography, or PET scans, exploit the high sugar uptake of cancer cells to pinpoint their location in the body. By tracking the metabolic activity, doctors can identify not just the presence of cancer, but also its exact location and even its stage. Patients are injected with a slightly radioactive sugar molecule, known as a radiotracer. This radiotracer travels through the bloodstream and is absorbed by cells that are metabolically active. Cancer cells, with their insatiable appetite, absorb the sugar at a much higher rate than normal cells, lighting up on the scan. These bright spots on the PET scan images indicate areas of high metabolic activity, which are often associated with cancerous growths. This allows medical professionals to detect and diagnose cancer with greater accuracy and speed, ultimately leading to better patient outcomes. Section 6. The pyruvate kinase switch, fueling growth or normal function. A key player in sugar metabolism is an enzyme called pyruvate kinase. It comes in two main forms, PKM1 and PKM2. Healthy cells primarily use PKM1, which promotes efficient energy production. Cancer cells, however, switch to PKM2. This switch favors the inefficient breakdown of sugar, producing lactate and the building blocks needed for rapid growth. Section 7. Cancer's shifting sands, adapting and rewiring metabolism. Cancer cells are masters of adaptation. They can rewire their metabolism to survive even in the harshest environments. This makes treating cancer incredibly challenging. Targeting a single metabolic pathway is often not enough. Cancer cells find ways to compensate. shifting their metabolism to utilize other energy sources. Section 8. Starving the beast, targeting multiple metabolic pathways. To effectively starve cancer cells, researchers are now focusing on targeting multiple metabolic pathways simultaneously. This multi-pronged approach aims to cut off all potential energy sources for these rogue cells. By combining drugs that inhibit different steps in sugar metabolism, scientists hope to effectively shut down cancer's ability to grow and spread. Final thoughts: the future of cancer treatment, exploiting metabolic weakness. Cancer's reliance on altered sugar metabolism offers a unique opportunity. This metabolic quirk, often referred to as the Warburg effect, means that cancer cells consume glucose at a much higher rate than normal cells. This dependency on sugar for energy can be their Achilles heel. By understanding the intricacies of these metabolic pathways, we can develop targeted therapies that exploit this vulnerability. Researchers are delving deep into the biochemical processes that fuel cancer cells, aiming to disrupt their energy production. This involves not just cutting off their sugar supply, but also interfering with other key nutrients and metabolic processes they rely on. The goal is to starve cancer cells, to cut off their energy supply, and halt their relentless growth. This approach is akin to laying siege to a fortress, cutting off all supply lines until the enemy is forced to surrender. By targeting the unique metabolic needs of cancer cells, we can create treatments that are more effective and less harmful to normal cells. While the fight is far from over, the future of cancer treatment may lie in exploiting the very processes that make these cells different from our own. This strategy holds promise not just for treating cancer, but also for preventing its recurrence, offering hope for a future where cancer can be managed more effectively and with fewer side effects. Thanks for watching. Don't forget to like and subscribe, and we hope to see you again in our next video.